Welcome to Study Loop.
Okay, so we know equivalent dose can be equal to N over M times RB gamma E gamma plus RB E E. If we do some arrangement here, we have N is equal to equivalent dose times M over RB gamma times E gamma plus RB E times EE. N here is the remaining number of the nucleus for the isotope here. And we know M here is the mass for the body tissue. And RB gamma here is the RB value for the gamma rays. And E gamma here is the energy of the gamma rays. And we know RBE here is the RBE value for the electron. And EE here is the electron energy. So we know equivalent dose is given as 3.5 sieverts. Mass of the tissue is 1 kilograms. And the RBE value for the gamma rays is 1 sievert per gray. And the energy that is transferred from the decay to the gamma rays is equal to 0.66 mega electron volt, which is equal to 1.056 times 10 to the power of a negative 13 joule. And we know RBE for electron is 1.5 sievert per gray. The energy transfer from the decays to the electron is equal to 0.51 mega electron volts, which is equal to 8.16 times 10 to the power of a negative 14 joule. So now we can plug in values to determine the remaining number of nucleus, which will eventually give us the value for the remaining number of nucleus is equal to 1.535 times 10 to the power 13. So now let's determine the amount of nucleus, in other words, the amount of atoms that is required to present in each kilograms in this case. So we need to set up such equation here, which is N equal to N0 times e to the power of negative lambda t. And we know lambda is a decay constant, which can be expressed as natural log 2 over T1 half. T1 half here is the half-life. So eventually have N is equal to N0 times e to the power of negative natural log 2 over T1 half times T. If we do some arrangement here, we have the initial amount of atoms, which is N0 here, which is also the required amount of atoms that need to be presented in this case is equal to N over e to the power of natural log 2 over T1 half times T. So we know N is equal to 1.535 times 10 to the power 13. And we know the half-life for such isotope is 30.07 year. If we convert to week, it's about 1563.64 weeks. And we know the time is given as 1 week. So now let's plug in back to the equation to determine the required number of atoms that need to be represented in this case. So this is equal to 1.535 times 10 to the power of 13 over e to the power of natural log 2 over 1563.64 week multiplied by 1 week. And this is equal to 1.536 times 10 to the power of 13. Okay, so 1.536 times 10 to the power 13 atoms will need to be present in each kilogram of body tissue. Okay, and this is the answer for this question.